Module 8, Kruskal-Wallis Test. A Kruskal-Wallis test is essentially an extension of the Man-Whitney-U test to more than two groups. Is a rank-based, non-parametric test that can be used to determine if there are statistically significant differences between two or more groups of an independent variable on a continuous or ordinal dependent variable. This test is a non-parametric counterpart of the one-way ANOVA. It is essential to realize that the Kruskal-Wallis H-test is an omnibus test statistics and cannot tell you which specific groups of your independent variable are statistically significantly different from each other. It only tells you that at least two groups were different. Since you may have 3, 4, 5 or more groups in your study design, determine which of these groups differ from each other. Assumptions. When you choose to analyze the data using a Kruskal-Wallis H-test, part of the process involves checking to ensure that the data you want to analyze can be analyzed using a Kruskal-Wallis H-test. You need to do this because it is only appropriate to use a Kruskal-Wallis H-test if your data passes the 4 assumptions required for a Kruskal-Wallis H-test to give you a valid result. In practice, checking for these 4 assumptions adds a little bit more time to your analysis. Before we introduce you to these 4 assumptions, do not be surprised if one or more of these assumptions are violated when analyzing your data using SPSS statistics. This is not uncommon when working with real-world data rather than textbook examples, which often only show you how to carry out a Kruskal-Wallis H-test when everything goes well. However, do not worry. Even when your data fails certain assumptions, there is often a solution to overcome this. 1. Your dependent variable should be measured at the ordinal or continuous level, such as the interval or ratio. 2. Your independent variable should consist of 2 or more categorical independent groups. 3. It would help if you had the independence of observations, which means that there is no relationship between the observations in each group or between the group themselves. 4. To know how to interpret the results from a Kruskal-Wallis H-test, you have to determine whether the distributions in each group, like the distribution of scores for each group of the independent variable, have the same shape, which also means the same variability. The Kruskal-Wallis test is applied to problems with the following characteristics. 1. Problem objective. Compare 2 or more populations. 2. Data type. Ranked or quantitative but non-normal. 3. Experimental design or the independent samples. Test statistics. Number 1. Rank all observations with 1 as the smallest observation and n as the largest observation, where n is equal to n sub 1 plus n sub 2 plus n sub 3, and so on. In the case of ties, average the ranks. 2. Calculate the sum of the ranks for each sample, denoted SR1, SR2, and so on, where K is the number of populations. Look at the formula. Examples. To compare three programs in traditional, hands-on, and pre-algebra classes, a mathematics committee decides to choose 21 similar students and randomly assign them to one of the three classes, 7 to each class, and then give them the algebra readiness test after the class. The data from this test for all 21 students are shown in the table. The research hypothesis using this data states that the populations producing these three samples are different. Look at the table. Solutions. As mentioned earlier, the Kroskal-Wallis test is the same as the Mann-Whitney-U, but it is used with more than 2 samples. With this in mind, what do you think is the first step in conducting a Kroskal-Wallis test? You should combine the scores and rank them. The 21 scores from the algebra readiness test in the example is ranked. Take a look at this. You can refer to these rankings as you use the following formula to compute the Kroskal-Wallis test statistics, which is called H. SR sub 1 is the sum of the ranks for sample 1, which is 53. SR2, the sum of the ranks for sample 2, which is 77. SR3, the sum of the ranks for sample 3, which is 101. N sub 1 is the number of score in sample 1, which is equal to 7. N sub 2 is equal to the number of scores in sample 2, which is also equal to 7. N sub 3 is the number of scores in sample 3, which is also equal to 7. The total, or the N, is the total number of scores in all the samples, and this is equal to 21. K is the number of groups, which is 3. Step 1. Substituting these values into the formula, and it will give you this. Step 2. Compute for the DF. Step 3. To look for the critical value, use the chi-square table. Here now is the Kroskal-Wallis results. Decision: accept the null hypothesis. Therefore, there is no significant difference between the samples drawn for 3 different classes, since the computed H value of 4.345 is lesser than the critical value of 5.991 at the 0.05 level of significance. Number 2. Does the workers' level of anxiety over domestic problems affect their performance at work? Use 0.05 to test the null hypothesis. Look at the solutions on how this particular question is being solved. can refer to these rankings as you use the following formula to compute the Kroskal-Wallis test statistics, which is called H. Where SR1 is equal to the sum of the ranks for sample 1, and that is 86. SR2, the sum of the ranks for sample 2, which is equal to 282.5. SR3, the sum of the ranks for sample 3, equals 334.5. N sub 1, the number of scores in sample 1 is 12. N sub 2, the number of scores in sample 2 is 13. And N sub 3, the number of scores in sample 3 is 12. The total, or N, the total number of scores in all the samples is 37, while K is the number of groups, and that is 3. Step 1, substituting these values into the formula gives you this. Step 2, compute for DF. Step 3, to look for the critical value, use the chi-square table. So here is now the Kroskal-Wallis results. Decision: reject the null hypothesis. Therefore, the workers' levels of anxiety over domestic problems affect their performance since the computed H value of 30.715 is greater than the critical value of 5.991 at the 0.05 level of significance.